Okay, in this lecture, we will learn about properties of Laplace transform. So, the very first property of Laplace transform is the linearity property. Linearity property that if you have the two functions in time domain and you sum up the scaled version of these two functions in time domain, it means that we have the same scaling factor in Laplace domain. So also we can sum up the Laplace transform of these two functions. So this is the linearity property. And also one thing we need to take care about is the region of convergence, because the region of convergence will be changed. Region of convergence is the region where the system is stable, and the region of convergence for this x1 of s is R1 and x2 of s is R2. So what will be the region of convergence for this function ax1 of s plus bx2 of s? That will be the intersection of two region of convergence. So the linearity property we can prove by definition, but actually, in fact, the integral has the linearity property. So we can say that this is the justification for the linearity of the Laplace transform. So also we can have the sum of two signals as a linear combination by this method. So the next property is the time shifting property of the Laplace transform. So for example, we have a Laplace transform pair, x of t and x of s. So the region of convergence is R. So when we shift the signal in time domain, so the magnitude and the phase of this x of s will be changed by this factor or by this exponential. So in fact, the region of convergence is still R. So the region of convergence will not be changed. So we have to find the Laplace transform of this function. So which property we will use? Definitely, because this is f1 of t, f2 of t and f3 of t. And we will take the Laplace transform f1 of s, f2 of s and f3 of s. And then we scaled up by the same factor as they are scaled. So in the last lecture, we learned the Laplace transform of delta of t, u of t and e minus 2t. So this is the direct delta function, this is the unit step function, and this is the exponential function. So this is exponentially decaying function because the value of t is greater than equal to 0. So we have the Laplace transform of f1 of t, and we have the 2 into Laplace transform of u of t minus 3 into Laplace transform of e minus 2t, and this is unit step function because of the reason the time is greater than equal to 0. So we will multiply it by the unit step function, and that is the exponentially decaying function. So the value or the Laplace transform of delta of t is 1, and the Laplace transform of u of t is 1 by s, and the Laplace transform of e minus 2t is 1 by s plus 2. So now we have this function in the form of partial fraction. So we will find the numerator and denominator polynomial from this 3 Laplace transforms. So the value of this is s square plus s plus 4 and s into s plus 2. So the convolution property, actually, if we have the convolution of two functions in time domain, so it's the multiplication of their Laplace transforms in the Laplace domain. So the region of convergence of these two is R1 and R2. So the region of convergence of this multiplication function will be the region of convergence is the subset of the intersection of these two region of convergences. So next we have the time differentiation property. So time differentiation property is that if we have the second, if we have the first order differentiation, df by dt, so this function is s f of s, right? So that value is n is equal to 1, and that is s1 f of s, and that value is s0 f first derivative of 0 minus. So this is in fact is, if we have the nth order, so we have the Sn minus 1 f 0 negative and Sn minus 2 f first derivative of 0 minus, and similarly we have the S0 f n minus 1 derivative, n minus 1 derivative 0 negative. So actually this is in fact this differentiation is representing, that part is representing the initial condition of the system. So the frequency differentiation is, for example, if we have the Laplace transform of t f of t, so it will be the differentiation in frequency domain. So that is d f of s and d of s. So here we have the differentiation in time domain, and here we have the differentiation in frequency domain or in the Laplace domain, right? So what about the integral? If we have the integral in time domain, so its Laplace transform is f of s by s. So here you have the, for the differentiation, you multiply it by the s, and here you divide it by the s. So for example, we have to take the Laplace transform of this function t square sine 2t u of t. So it is in fact is t n f of t u of t. So how you can take the Laplace transform of this function? For this, you know that the sine 2t has in fact is the Laplace transform pair omega s square plus omega square. And if the value of omega is 2, so we have sine 2t is omega 2 s square plus 4, right? So now we have the Laplace transform of t square sine 2t. So for this we use this relationship which we learn in the last lecture, that t n f of t is minus 1 raised to power n, and the differentiation in frequency domain is dn by f of s. So it will be in fact is we have the minus 1 square and the second order derivative. So second order derivative of this 2s square plus 4. So we will take the derivative. So we will get the value of minus 4 by s square plus 4 square, and we take the derivative again, and we have the s square plus 4 cube and 12s square minus 16. So this is the Laplace transform of this function. So actually the Laplace transform is equal to the Fourier transform when s is equal to j omega. If s is purely imaginary, so we have the Fourier transform equivalent to the Laplace transform. So we take the value of Laplace transform by replacing s by j omega and e minus st, and this is the Laplace transform by definition as we have learned in the last lecture. And what about if we want to transform it in the time domain from this frequency domain? So we multiply it by e st and we divide it by 1 by 2 pi. So this is what we have learned in the Fourier transform property. When you substitute the value of the when you substitute the limits from sigma minus j omega to sigma plus j sigma minus j infinity to sigma plus j infinity, so it will we have the j component here. So x of t and x of s will be the uh, uh, Laplace transform pair. So what about the region of convergence? So the region of convergence, when we have the value of sigma 1 plus j omega, when omega is from minus infinity to infinity, so we have the region of convergence is sigma 1 under sigma c, because the value of omega is varying from minus infinity to infinity, and the value of sigma 1 is under the region of convergence. So actually the derivation of this inverse Laplace transform is beyond the scope of this course, but you can consult signal and system book to see the derivation of it. So, but we learned that how to take the inverse Laplace transform. Actually, we use the inverse Laplace transform pairs to take the inverse Laplace transform. So we have seen a lookup table for these transform pairs. For example, we have to take the inverse Laplace transform of this function. So we have 3 by s minus 5 over s plus 1 plus 6 by s square plus 4. So I will give you a few minutes to think about, and then I will show you the solution of it. You have seen that these are in fact is the functions using summing up using the linearity property, and we have to take the inverse Laplace transform of individual functions. So u of t is 1 by s
सर आवाज नहीं आ रही है। सर म्यूट है. अब तो
So we have seen that the unit step function has a Laplace transform pair with 1 by s, and e minus at u of t makes a Laplace transform pair with 1 over s plus a. So sine of omega t u of t makes a Laplace transform pair with omega s square plus omega square. So these three functions are in fact f1 of s. So we take 3 common, and 1 over s has a Laplace transform u of t. So that is 3 and u of t. What about the second part? So we take the inverse Laplace transform of 5 over s plus 1. So this is in fact is minus 5 e minus t. Now we have plus 3 sine 2t u of t. So this is in fact is a Laplace transform pair with 3 sine 2t u of t, right? So in that way we take the inverse Laplace transform pair. So this Laplace transform is given in the form of partial fraction. If we don't have the partial fraction, so first we take the partial fraction of the Laplace transform given, and then we take the inverse Laplace transform. So we see an example. For example, we take another function as we have seen here. Let me check some function. For example, if we have the this Laplace transform and we want to take the inverse Laplace transform of this. So first we perform the partial fraction, and then from partial fraction we take the inverse Laplace transform back to this. So this is how we take the inverse Laplace transform. Now we see the properties of Laplace transform. So far we have learned the linearity